Great to have all of you here. So firstly, I'll just say thanks for everyone for joining. This is going to be just a little bit of experimentation and fun things that I had to or were able to work on for my project presentation for honors, which is going to be next week, Tuesday. So if Rocco, if you're keen on that, or Ralph, if you're keen on that, just give me an indication. I can send you guys the link to the formal presentation. This will just be a little bit of fun stuff about it. So as all of you saw, the title said almost a pie and other approximations. So everyone has seen the approximation for pi, that pi is roughly 22/7. So everyone saw this approximation for pi from school. Teachers would always say, do this calculation and use 22/7. Now, pi is equal to 3.14159265358, so on, so on, so on. And 22/7 happens to be 3.142 and then some more. So we see that where it differs from pi is on the third decimal. And that's a pretty good approximation given that it's just 22/7. It's not 3,142/1,000. It's just this. Now, the example that I gave just now, 3,142/1,000, whatever this one here is, if we were to take 3,141, this is probably a better estimation already, or approximation, but it's not elegant the way that is. Now, the next elegant approximation for pi happens to be 355/113. The reason why this is also an elegant approximation is because this is equal to 3.14159 so on. So it differs from pi only on the 1, 2, 3, 4, 5, 6. It is correct up until the 6th decimal. It only differs on the 7th one, which is again amazing given that it's just this. It's not some 3 million over 1 million fraction. So this is also a good approximation. And in fact, you get an endless list of such good approximations for pi. And this is actually true for all of the irrational real numbers. You get this good list or sequence of approximations for this irrational number by some rational number. And about this, how do we get this list of good approximations? So this is where continued fractions come in. So continued fractions, say if we have some alpha, that's a real number. Let's just keep it real, not irrational for now. So we have some alpha. This alpha can be expressed as some a. Where's my ruler? As some a, 1/some b, plus 1/some c, plus, and you get this kind of staircase effect here. Now, if alpha happens to be rational, if alpha is equal to some p/some q, if it's rational, then these steps are going to be finite. It's going to go up until some an minus 1 plus 1/an would then equal this p/q. But if alpha is an element of the irrationals, then this staircase effect will go on infinite. Then it will in fact be called an infinite continued fraction. Now, pi being irrational, it has an infinite continued fraction. And the way you get these is as follows. So if you take pi, right, you get 3.14, so on. And you take the floor of pi, which is just the largest integer smaller than pi. So that's going to be 3. So what you then do is you take 1 over pi minus its floor, which is 3. And that's going to be 1 over 0.1415, so on. And that is in fact going to equal 7,0625, so forth. So we got this 7 here. Now, our first one, let me put this on the side. So our first element in this continued fraction is 3. That's pretty clear. And then our next one in the continued fraction of pi is going to be the floor of what we got here, so 7. If we now take this again and we make this even more complex, like here, I think I'm still on the screen, yes. And we do this, then we're going to get another integer, or sorry, not integer, another real number, and the floor of that real number is going to be the next one. So this just happens to be 15.99 something, and the floor of that, even though it's very, very close to 16, we take the floor always, so it's going to be 15. So the next one's going to be 15, and you get the idea. It continues like that. So this is how you get the continued fractions, the continued fractional elements of any irrational number. And wherever you cut it off is where the next good approximation is going to be. And in fact, these approximations are called convergence. So, for example, the first convergent, I'll explain now. Sorry. The first convergent is just going to be P0 over Q0. I'll explain what P and Q is in a moment. The first convergent is going to be 3. That's just the 3 part of the continued fraction elements. The next convergent is going to be if we stop at 3 plus 1 over 7, which is going to be 22 over 7 as we got. So the next one is 22 over 7. And continuing in this manner, we'll find that this is where the fact that this was very, very close to 16 comes in, is the third convergent is something very close to what we had previously, 355 over 113, but the it's going to equal something. But in fact, the third one, sorry, I'm getting confused here with my numbering. The third one is something. The fourth one is going to be that 355 over 113 that we had. And this continues like this. So that's how you get these good approximations, and that's how you get almost a pi, as the title kind of hinted at. So let me now explain what these P and Q are. Let me just stop here first before I explain that. Is there any questions right now about any of this? Okay, then I'll just continue. So we have this P sum n and Q sum n, and we have that the convergents are going to be Pn over Qn. Now, what these are defined as follows. So if we have alpha Is that on the screen? I need to keep track of what is on the screen and what isn't. So if we have that alpha is equal to a plus this staircase here, a, b, c, so on, p0 is always going to be the first one. So p0 is always going to be a. p1 is going to be the first one and the second one multiplied together plus 1. And then we'll find that for any other n, where n is larger or equal to 2, it is going to be the nth element in this. So the third one is C and the fourth one is D, times Pn minus 1 plus Pn minus 2. And for Q0 is going to be 1. So you see that for pi, then it's just 3 over 1, which is 1. For Q1, it is going to be the second element always. So Q1 is going to be B. So if we look here, P1 is AB plus 1. 3 times 7 plus 1 is 22, divided by 7. So this holds for pi. And then for Qn, we have that it's very much similar to the Pn case. And all this is for n larger or equal to 2. So this is how you construct the convergence. The convergence isn't Pn or Qn. It's the division of Pn by some Qn. This is the nth convergence. So that's how this goes about. Now, I'll get back to all of this in a moment. I'm just going to explain briefly why this is quite interesting for us. Is when we work in computer science, right? Actually, let me use as a reference pi, for example. When we work in computer science, is in coding, it's very hard to use irrational numbers. Like pi, you would think is well used by a computer because they have stored up until, I don't know, the thousandth digit in the decimal or even more, but it's still actually just an approximation. You know, ints and longs in computing, it has its certain limits. So that's where it comes helpful in order to approximate irrational numbers by very good, easily calculatable fractions in order to make calculations easier and yet still reliable. So that's the usage of why we're doing this. Okay, now let me continue from that. So this whole time we're talking about approximations, right? This whole time we're talking about approximations, and we're saying this is a good approximation and that isn't, and so on. But we need to have a certain inequality, let's say, in order to say whether it's good or not. So an absolute value. So a good approximation for some real number alpha is if the difference between it and the fraction that we choose to approximate it by, let's say, is smaller than some value here. Now, let's think what this value is. If this value is just going to be some value c, then there's going to be infinitely many of these, and they're not going to get better. They're just going to get bigger fractions, but they won't become any better approximations. So let's think maybe if it's c divided by q, maybe this is a better approximation. So in this case, what we would get is alpha q minus P is less than C, then this is what we're working with. But still, there's going to be infinitely many approximations for this, for any alpha and C that you choose. They're all going to be very close to between 0 and C, but they're not going to necessarily get better again. So if we up the ante a little bit, and we make it that it's C divided by Q squared, this is where it gets interesting. This is where we get possibly a sequence of these good approximations, which each one in the sequence happens to be better. So in this case, we would have alpha Q squared minus PQ, the absolute value is less than this C. And I think just from observation and maybe a little bit of playing around, you would find that they get better. And this is true for pi as well. So now I said that if it's just Q, then there's infinitely many. And if it's Q squared here, maybe it's infinitely many, but maybe there exists a C small enough such that there are actually only finitely many, which is, it's a bit strange. Suddenly we can only get a finite sequence for some C. So let me take this one example just to prove my pointer. If we take alpha to be the golden ratio, so that is 1 plus square root 5 over 2, right? If we do this and we try and approximate the golden ratio by some convergence, some fractions P and Q, I just gave away the game there, by some fraction P divided by Q and try and get it better, there's a formula that we have which says the following, which will be of a lot of use to us in calculating what this C might be, where for any C larger, for any C star larger than or equal to this C, there's going to be infinitely many possibilities for this P and Q, but any C star smaller than this C and larger than 0, there would only be finitely many. So we have a theorem that's going to help us a lot here. And this theorem is as follows. So if we have alpha, let's have it be irrational, and and we have that for some P and Q that are integers, where Q is larger or equal to 1, Q needs to be positive. If we have that the absolute value of alpha minus P divided by Q is less than 2Q squared, so our C is a half in this case. If this is true, then P and Q is a convergent of alpha. So what that basically means is there exists some n natural number such that the convergent Pn over Qn of alpha is equal to this P over Q. Okay, I'm not going to go into the proof of this, it's quite lengthy, but we have this now and we can use this. And looking at this, then we can apply this there. So first of all, now we know that C, if the C exists such that for any C star smaller than C it's finite, then the C is going to be less than a half necessarily. Okay, now let's think here real quick. How do I want to go about this? Okay, so It's going to take a little bit of a while, but let's do it anyway. Okay, so I have this here, and we can give it a PNQN because we're going to take a C that is in that range, right? Okay, now from the convergence, from the linear recursion that we have for calculating QN, just write that again so everyone can see that. From this linear recursion for calculating Pn and Qn, this is what we're going to use to try and find what the C is. So first of all, we need to try and find out what the continued fraction elements are of the golden ratio. And interestingly enough, it is going to be the simplest one that there is. So first of all, we have that it's 1. And that's going to be a 1 as well. And that's going to be a 1. And that's going to be a 1. And so forth. Easiest continued fraction ever. And we can write this just to make it easier for ourselves as 1, 1, 1, 1, 1, so on. This first one is that one. The second one here is that one. Third one is that one, so on. So we have this. And from this, we can now use our linear recursion for Pn and Qn to find the characteristic equation for, excuse me, for finding a general solution for what this Pn and Qn is going to be. Now, the characteristic equation from these two be the following. How do we get this? It's simply by assuming x squared is Pn, x is Pn minus 1, and 1 is Pn minus 2. So each iteration, we increase the power of x. And then we take everything over to the one side, and since all of the continued fraction elements are going to be 1, an is going to be 1. So that's how this then turns into x squared minus x minus 1. Okay. Now, using the quadratic formula, we're going to find that x is equal to 2, that's going to be 1 plus minus, and that's going to be 5. So we have that x is equal to the golden ratio itself and its conjugate, which is just 1 minus square root 5 all divided by 2 instead of 1 plus square root 5 over 2. So x is equal to alpha or alpha conjugate, alpha bar, which is just the conjugate of alpha. Okay. And what we're now going to do is we're going to find, using P0, am I still on the screen, guys? P0 and P1 and Q0 and Q1, we're going to use these to try and find values for the following. So using some combinatorics, I'll again save the proof why this is true, but using some combinatorics, we would find that the general solution is going to be some constant x times one of the values, so 1 plus square root 5 over 2 to the n, plus some other constant y times the other value, so 1 minus square root 5 over 2 to the n. And similarly for Qn, let's make that xp and yp. Similar for Qn, we're going to get some xq, same thing, yq, same thing. And we now want to find what this xp and yp is going to be. Okay. Now, again, just saving a lot of calculations because we have limited time. What this evaluates into is the Binet formula, which is going to be the following. Just not sure. Excuse me, I just want to make sure that I don't write this down wrong. Okay, so the Binet formula is going to be the following. We're going to have alpha n minus the conjugate of alpha to the power n, all of this divided by 5. That's just from plugging in the value of p0, which is just going to be 1, and p0 is equal to 1 is equal to xp plus yp, and then making xp the subject, and then taking p1, which is going to be 2, so and then calculating from that the simultaneous equations and finding what xp and yp is, and then the same thing using q0 and q1 to find what xq and yq is. And then we're going to find that for p. For p, it is going to be the Binet formula. And this, coincidentally, is also going to be the one for qn minus 1. So if we want to get qn, q, is it n minus 1 or n plus 1? Sorry, qn plus 1. So if we want to get qn, that's just going to be to the power n minus 1 minus alpha conjugate to the power n minus 1. Now just remember that alpha is equal to 1 plus square root 5 over 2, and alpha bar is equal to 1 minus square root 5 over 2. Okay. So we have this formula here now. Okay. And we want to try and use this general formula for Pn and Qn to find what the C is going to be. So to make C the subject here, we're just going to multiply by Qn squared all the way through. Okay. And in order to find what the C is, we want to have that as we increase n here, this absolute value gets closer and closer to C, but it still remains less. So we're not sure that the limit for this exists. so we'll at least take the lim nth of this absolute value here. And the lim nth, which is just the lim infimum. Apologies if not everyone knows what the lim nth is, but it will in fact be that the lim nth of this here is going to equal C. Okay, so very strenuous calculations will follow from here. So this is alpha. We had that yes, we had that Qn is square root 5 alpha n minus alpha bar n minus 1. That should be a 2. P is just going to be the power n. And then we're going to try and simplify and see what we find. This is going to be a lot of expansion, a lot of simplification, because yeah, there's just a lot to do here. I'll spare everyone the boredom about this. But what this is ultimately going to get to is we're going to find that this value, after a lot of simplification and expansion and things, is going to be 1 over square root 5. Through a lot of rigor and everything. So we're going to find that C is equal to 1 over square root 5. So from this, if we have 1 plus square root 5 over 2 minus PQ, P squared. If we have this inequality, then what would we take from C being that value? If we have this inequality, first note that square root 5, it's 2.23, I believe, which is larger than 2, and therefore suffices for the previous theorem that we had, which said that all the P over Q that suffice for it will be convergent. So since this is the case, all the PQ are going to be convergent, right? And from the C, we have that for the C, there's going to be all the convergence of the golden ratio 1 plus square root 5 over 2. All the convergence will suffice for this, or at least an infinite amount of the convergence. Maybe not all of them, but picking out a few, there will at least be infinitely many that converge for it. And any value larger than 1 over square root 5. Any value larger would of course be true as well, because all of these are true for 1 over square root 5. But if we were to take anything smaller than this, if we were to take our C star to be smaller than this, we would find that there are only finitely many, for lack of a better word, good approximations. For 1 plus square root 5 over 2. And the reason this is true is going back to what the lim and what the lim means for us. Is this is going to, for its lim reach 1 over square root 5. So if we were to take any c star smaller than 1 over square root 5, eventually, for some n, say larger than or equal to some big N, eventually we're going to have that this absolute value will be larger than this c star. It would be between c star and 1 over square root 5. And therefore we can't take it. And any n larger than that, it would get closer towards 1 over square root 5, and thus it would still be greater than c star, and so there are only finitely many of these possibilities. So, so this was a very specific example. Square root 2's continued fraction is going to be 1 plus 2, 1 plus 1 over 2 plus 1 over 2 plus 1 over 2 plus so on. So another nice one to test this out with is square root 2. And if you go through the same process, you're going to find that the c for square root 2 is going to be 1 over 2 square root 2. So again, 1 over 2 square root 2, that's it's less than a half. So all the p and q are going to be convergence, and then again, by the same reasoning, if you take anything smaller, it'll only be finitely many good approximations for this. Now, here's the final result that we get from this is finding this for any, or at least attempting, for any element of the form a plus some square root of some discriminant divided by 2 is finding what its c is going to be. And although I haven't found it yet in my project for any of these, for any continued fraction of the form a, b, c, d, so on, I have managed to find the general solution for a one periodic continued fraction, which just means it has a period of 1, so every single element is the same after some point, and specifically from the second element, continued fraction element onwards. So I did find a way to calculate it for all the ones of this form here. Still on the screen, great. And simply by taking the same approach that I did above, but in the general case, and then through a lot of simplifications and solving, we would find that if alpha is equal to this, then our c, the constant that we're looking for, is going to be one of the following. Okay, so we're going to have 3 cases. We're going to have the case where b is negative. Let me just make that a note. A and b are still integers in this case. We're going to have 3 cases. We're going to have where b is negative. We're going to have where b is, or not, sorry, not b. We're going to have the case where, what did I get again? Okay. Where alpha is between the square root of the discriminant over 2. Just make a note that this is b squared plus 4 over 2. And we'll have the otherwise case. Okay. So in the case where b is negative, the c is going to be 4a plus square root d all divided by d. C is going to be the absolute value of that. If alpha is such that this is the case, then we're going to find that it's just 1 over square root d. And for any other case, oh no, sorry, I swapped these two. Sorry. For any other case, it's 1 over square root d. And in the case where alpha is greater than 0 but smaller than square root d divided by 2, this is going to be d. Just find where I calculated that. Okay. 4a minus 2b plus square root d. I'll just write that nicer over here. Okay, so this took quite a while. Apologies, but this is the 3 cases that we're going to get to eventually. And these are excluding, if you check this out a little bit closer, then you're going to find that C is going to be one of these 3. If we look at the 2 examples that we had earlier, so if we take square root 2, then square root 2 was equal to 1, 2, 2, so forth. B is not negative, and alpha, which is 1.41, is less than the discriminant about the square root of the discriminant divided by 2, which is square root of 8 divided by 2, which is yes, which is going to be 2 square root 2. So square root 2 is indeed less than 2 square root 2, and therefore it falls into the other case, which is 1 over b squared plus 4, and this was 1 over square root 8, which is equal to 1 over 2 square root 2, which we got. And if we take the golden ratio, 1 plus square root 5 over 2, we would find that it also falls into this camp over here, and that's why we got 1 over square root 5. And that's it. The rest I'm still working on. I'm still trying to figure out the case for when it's one periodic but it doesn't start immediately. So where we have that it goes up until some k and then it starts repeating itself. Still working on that one, but we'll see how that goes. And also still working on the part of where it's 2 periodic, so where it starts with some A and then goes B, C, B, C, B, C, so on. Trying to figure out what their C is going to be. And yes, that's it. Does anyone have any questions?
So you have C over Qn squared. is it possible to do better than that, like Qn to the 3 or to the 4? Or?
No, that's a very, very good question. So you're asking, right? Q2 plus some epsilon, right? Or let's say epsilon is positive. So this, considering this, any better trying approximations, there's a theorem that Roth actually showed back in 1953, I believe. So Roth's theorem, and he won a Fields Medal actually for showing this. He showed that if alpha is algebraic irrational, the algebraic just means that alpha is a root of a polynomial, some polynomial in integers. If alpha, then any sequence for a P and Q for which this would be true would be finite. So it doesn't matter what C is. So for all C greater than 0, that inequality will have finitely many solutions P divided by Q. Is that sufficient for your question?
Yeah, thanks. That's pretty cool.
There's another theorem which is basically the reverse of this, which is the Liouville theorem, which interestingly enough goes the other way, is where he says absolute value of alpha minus P over Q larger than C P squared. There exists he says that for this inequality, there exists a C larger than 0, such that this holds for all P over Q. So any rational number this would hold for. And this kind of stems from the result that we got earlier, is we found that there is some C for which anything smaller would have finitely many solutions. So if all the solutions for some C star smaller than the C that we found, if all the solutions were P0 over Q0, so on up until P and Qn, for each of these we would find some absolute value alpha minus P0 over Q0, P and Qn. Each of these would be larger than 0, of course, because it's an irrational minus irrational. And this C that you're going to find, the C is going to equal just the minimum of this set here. And that's how Liouville's theorem is basically, or that's one way to prove Liouville's theorem.
Lourens, on Rolf's theorem, I'm not really sure what I'm talking about anyway now, but what's the, is there a significant difference in an algebraic irrational and what is it, a normal irrational? What's the difference between the two?
So let me just give a formal definition for what algebraic means, right? Is alpha is algebraic if there exists a polynomial an xn an minus 1 xn minus 1 so forth. If there exists some polynomial, and we can work in different domains, but I'm just gonna work in the integers. We can work in the rationals or the reals, but in this case, working in integers. Alpha is algebraic in the integers if there exists some polynomial. Let's call this polynomial px, such that plugging alpha in gets us 0, such that alpha is the root of this. So then where your question comes in is, are all irrational numbers algebraic, right? And it actually turns out that that is not the case. You do get algebraic numbers, which you do get some beta that is not algebraic. And in fact, this is the same as saying a beta that is transcendental. That's some more terminology. So if beta is not algebraic, then it is transcendental. So no polynomial that we can think of, it would be a root for. So for example, I'm not 100% sure about this, but maybe Professor van Wyk can correct me if I'm wrong, is pi is transcendental. I believe, I'm not 100% sure.
Yes, it is.
Great, thanks, Ralph. So there's no polynomial that we can create for which plugging pi in would give us 0. Does that answer your question?
That does answer my question, but why can't Ross theorem be used on pi, for example? Why does it use polynomials in his equation? Theorem, what? Oh, there's a okay. No, I understand.
Is that okay?
Yeah. It's quite amazing that pi can't be found by the root of some polynomial.
Yeah, there's a bunch of interesting things that happen with some of the numbers. Like pi has a very erratic continued fraction. If you write it out, there's going to be no pattern towards it. So we can't really use it because there's no pattern, then it's not going to be periodic. So and it being periodic, I haven't proven this, but it's a very strong hunch or a conjecture, is that in order for the C to be able to exist for this, again, not Ross theorem here, in order for C to exist for that inequality, we need to have that the irrational number is eventually periodic. And why that is pretty cool is because there's another theorem, Lagrange's theorem. I'm going off on a tangent here, so just stop me any moment. So Lagrange made many theorems, but this is one of them, where he said that if alpha is a quadratic irrational, this just means a root of this polynomial here. Alpha is a quadratic irrational if and only if its continued fraction. Am I still on the screen? Yes. If and only if its continued fraction is eventually periodic. And any root of a binomial like this, any root is going to have the following general form. So all of them will have that form. So at least all of them would just be some fraction plus some fraction times a square root. It's not towards some nth root of some d. All of them would be like that. And that's also that's like, if I can get this, then I am very happy for my project. If I can prove that it being eventually periodic, and thus a quadratic irrational, and thus of this form, that there exists a C such that, and then our whole inequality.